Now, let us discuss the speed of the sound wave. As we discussed in the introductory section, that the sound wave is a three-dimensional wave. So, in general, we have to analyze the propagation of the sound wave in three dimensions. But for now, we will look at the simplest model. That is, we will look at the propagation of sound wave in one dimension. That is, if we have the medium in this cylinder and we generate the sound wave by disturb the medium by moving the pistol here to generate the sound wave in the cylinder. So it is a wave in one dimension. Assuming that the velocity of the sound wave is v, and the wave will propagate in this cylinder with this velocity v. Please note that the velocity of sound wave can be very different from the velocity of the motion of the pistol here. Remember when we discussed the wave in the string, the velocity of the oscillation of the string can be very different from the velocity of the wave on the string. It means that the velocity of the motion of the medium in this case is the motion of the medium is created from the motion of the pistol. So the velocity of the motion of the pistol can be very different from the velocity of the sound wave. And in general, from the experiment, we know that the velocity of the sound wave is much larger than the velocity of the disturbance of the source of the sound wave. Okay. So, if we look at this figure, and v is the velocity of the sound wave, let us define the element of the medium here with the cross-sectional area A and the thickness equal to the v delta t. Delta t is defined as a small time interval. So this length is the length that the sound wave will travel from the left face of this element to the right face of this element. In the equilibrium configuration for the undisturbed gas, the pressure on this face of the element of this element and the pressure of on this face of this element are equal because the system is in equilibrium. And if we calculate the force from the pressure, the force from the pressure on this face is equal to the PAI. I is a unit vector point to the positive x. Here is point to the right. So PA is the magnitude of the force and I is the unit vector. So PAI is the force on the left. That is the force acting on the pistol, and the pistol exerts the force on this face of the element of the medium. And in the equilibrium configuration, since the medium is at rest, so it means that if we look at this face of the medium, we have equal magnitude of the force from the pressure, but in the opposite direction. So the force from the pressure on this face is equal to the minus PAI. Okay. Now, if we increase the pressure by apply some force on the pistol. So the pressure on the left face of the element increase from P to P plus delta P. And the force here is P plus delta P times A, pressure times the surface area times the unit vector. And during the time delta T, as we discussed before, that this length is the length that the wave will travel during the time delta T. So during the time delta T, the sound wave, the disturbance of the medium, will not reach the light side until the time pass equal to delta T. So we can say that during the time delta T, on this phase, the pressure of the medium is not changed because the sound wave does not reach this phase until the time delta T. So if we look at this element, we can say that on the left phase, the pressure changed from P to P delta P, P plus delta P. But on the right phase, the pressure still equal to P. The pressure is still equal to P, and the force on this phase is still equal to the minus P A I. Next, if this pistol moves with the velocity Vx, okay, it will disturb every molecule of gas in this region to move with the same velocity. Okay. Strictly speaking, this is not true because the disturbance from the pistol will affect the molecule of the gas near the pistol only, and the gas near the surface of the pistol will move with the velocity Vx, the same velocity as the pistol. But far away from the pistol, the gas may move with a different velocity. But if we consider the very small element of the medium, which means that if we take delta T to be very small, we can approximately assume that every molecule in this element, are disturbed by the pistol and move to the right with the same velocity of the pistol. That is, the velocity is Vx. Okay, this is valid only when delta T is very small. Now we will use the impulse momentum theorem to analyze this situation. Okay. Since there is a force from the pistol to this element of the medium, it means that there is the impulse on this medium, and this impulse must equal to the change of the momentum of every molecule in this medium. So we will have that the impulse on this element, is equal to the change of the momentum of every molecule in this element. The impulse can be calculated from the net force on this element. The net force on this element times the time interval that the force is applied to this element. So we can write that I is equal to the net force times delta T. But the net force, you can see that the net force is equal to the difference of this force and this force. So it's equal to the A delta P. You can see that P here and the minus P here cancel. So we have the net force equal to A delta P I times delta T. Okay, so that is the impulse. However, we have from the previous section that delta P can be written as the minus of the bulk modulus of the medium times the change of the volume over the initial volume of the element. The change of the volume of the element is equal to the motion, to the displacement of the pistol here, times the cross-sectional area of the pistol, right? We can see that we have this result because we assume that during the time delta t, the sound wave just reached the light phase of the element. So at this point there is no displacement of the element at this point because the sound wave just reached this point. So the motion, the displacement of this element happen only on this side, and the change of the volume is due to the motion of the displacement of this element on the left side. And during the time delta t, the motion, the displacement of the pistol is equal to the Vx delta t. So we have that the delta V is equal to minus Vx delta t times A. We need to put the minus sign here because the change of the volume is negative because this is compressed. Okay, so we have to put the negative sign here. And the initial volume of the element is equal to the cross-sectional area times this length, which we define and we assume the length here equal to the V delta t. So the volume is equal to the V delta t A. Okay, so we can see that A cancel, delta t cancel, and this minus sign cancel, and we have that this equal to the B Vx over V. And if we put delta P here to the equation of the impulse, we have that the impulse I is equal I is equal to A B Vx over V delta t times the unit vector I. Okay. We have the impulse equal to the expression. Now, we look at the right side of this equation, the delta P. Initially, there is no disturbance on the medium. So, the momentum of the medium initial momentum of the medium is equal to 0 on average, okay, because the medium does not move. After the disturbance from the pistol, every every molecule in this element are assumed to move with the velocity Vx. So the total momentum of this element is equal to the mass of this element times the velocity of the molecule inside this element. So we have that delta P is equal to the rho Vi, which is the total mass of the element, times Vx I, which is the final velocity of every molecule in the element, minus the initial velocity, average velocity of every molecule in the element, which equal to 0. So we have that is equal to rho Vx A delta T I. Now, if we equate these two equations, take I equal to delta P and do some algebra, you can see that we will have the final result that V must equal to the square root of B over rho. Okay, B equal to the square root of B over rho. Okay, if you put I equal to delta P and cancel the common factor, you will have that V is equal to the square root of B over rho, and that is the expression of the velocity of sound wave in the medium.